Hi, Huckleberry here, and today I'm going to teach you the basics of electronics so that you can understand it in a very intuitive way. In fact, if you enrolled in community college to become an electronic technician, this is pretty much what you'd learn in the first few weeks of your first class. We start with the idea that there are four fundamental properties of electricity that drive everything: voltage, current, resistance, and power. For the rest of the video, we learn exactly what these are and how they relate to each other. Hint, think Ohm's law. You may recall from high school science a simplified picture of the atom. At its center is the nucleus, which consists of uncharged particles called neutrons and positively charged particles called protons. And orbiting around the nucleus are negatively charged particles called electrons. The electrons are the important part for electronics. In order for us to generate electricity, we must apply energy to matter. When we apply enough energy, we can free some electrons. When this is done properly, we can get negatively charged electrons to flow through a material like copper or silver that we call a conductor. Electricity is simply the flow of electrons through a conductor. Next, we must understand that like charges in nature repel each other, while unlike charges attract each other. This, of course, affects the way that negatively charged electrons behave. Current is defined as the movement of electrons from negatively charged atoms to positively charged atoms. Current is abbreviated with the letter I. Current is measured in amps. Now, an amp is defined as 1 coulomb per second passing a single point. So, the obvious question is, what's a coulomb? It's simply a specific number of electrons, and a very large number at that. In scientific notation, it's 6.24 times 10 to the 18th electrons. That's 624 with 16 zeros after it. So current, which is the flow of electrons in a wire, can be visualized like water flowing through a pipe. Just as the flow of water through a pipe can be measured in gallons per second, electrons through a wire is measured in amps or coulombs per second. In order for current to flow, there must be some force that causes the current to flow. This force is called electromotive force, and it occurs when there is a difference in potential created in the circuit. Difference in potential just means that there is a negative charge relative to a positive charge at two different points in the circuit. This difference in potential is called voltage, and it causes current to flow from the negative to the positive. Voltage is measured in the unit called volts. Once you understand what voltage and current are, resistance is really easy to understand. It's the opposition to electron flow in a circuit. Resistance can be measured in ohms. Resistance is abbreviated with the letter R, and ohms are abbreviated with the Greek letter omega. To do any useful work, we need to get electricity to run through a circuit, which is nothing more than a complete path for current to follow. All circuits have at least three elements: A voltage source, for example, a battery, a load, that is something that does some useful work, for example, a light bulb, and a conductor, which is usually a wire. Here is an example of a circuit and our first look at a schematic. The component on the left is the symbol for a battery and obviously the voltage source. The short line at the bottom represents the negative terminal of the battery, and the longer one at the top is the positive. R1, R2, and R3 are the symbols for resistors, which are electronic components manufactured to have a certain resistance in ohms. Here, the resistors represent the load. Note that this is a specific type of circuit called a series circuit. And what makes it a series circuit is that there is only one path for the current to flow. The other type of circuit is a parallel circuit. In a parallel circuit, there is more than one path for current to flow. In terms of current flow, the only other type of circuit there is called a series parallel, which is nothing more than a combination of the two. So how can you figure out the total resistance in a circuit when you have more than one resistor? The answer depends on whether they are in series or in parallel. For resistors in series, we simply add the values. This makes sense if you use the analogy of traffic on a highway. Imagine a car is stuck in the right lane of a 3-lane highway. That's going to create a resistance to the flow of traffic. Now a mile down the road on the same highway, another car is stuck in the right lane. That's going to create another resistance to the flow of traffic. If you're trying to get home, it's obvious it's going to take longer if you had to pass 2 stuck cars than if you only had to pass 1. For resistors in parallel, it's less intuitive. In fact, if you had 2 resistors in parallel, the total resistance is actually less than if you only had 1. How can this be? Let's go back to our highway analogy again. Suppose on the main road you have a stuck car. That represents some resistance to traffic. Now suppose you build a second road next to the main road and parallel to it. Again, you have a stuck car in the second road. So now some cars can take the main road and some cars can take the second road. Now, even though the second road has some resistance, having 2 roads to take is still going to move more cars through than having only a single road. The formula for resistors in parallel is 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3 and so on. Ohm's law tells us the relationship between voltage, current, and resistance in a circuit. Ohm's law is stated in the formula E equals IR, where E equals voltage measured in volts, I equals current measured in amps, and R equals resistance measured in ohms. With a little bit of high school algebra, you can solve for the other 2 variables. Therefore, R equals E over I, and I equals E over R. Studying the formulas gives you an intuitive understanding of how the three quantities are related. Current is directly proportional to voltage and inversely proportional to resistance. This means that increasing voltage causes current to increase, but increasing resistance causes current to decrease. This makes sense when you remember that resistance is the opposition to electron flow, and when you remember that voltage is the force that causes current to flow. Now is a good time to introduce a new term called voltage drop, which is simply the difference in potential across a resistor or group of resistors. We can measure the voltage drop with a voltmeter simply by placing the leads of the meter across a resistor. Now let's look at some circuits to see exactly how Ohm's law operates. Let's take some current readings using an ammeter. To read current, we need to open the circuit because current is the flow of electrons through a conductor. Ammeter number 1 equals 0.01 amps. Ammeter number 2 equals 0.01 amps. Ammeter number 3 equals 0.01 amps. Ammeter number 4 equals 0.01 amps. So we see that the current is the same wherever you measure it. This is no coincidence. In a series circuit, the current is always the same wherever you measure it. This makes perfect sense because there is only one path for the current to flow, so it would have to be the same everywhere. Expressed in a formula, I total equals I1 equals I2 equals I3. Let's take some voltage readings using a voltmeter. Since voltage is just a difference in potential, we take the readings across the resistor. Using the voltmeter across R1, we measure 1 volt. Using the voltmeter across R2, we measure 5 volts. Using a voltmeter across R3, we measure 10 volts. If we add up the voltage drop across R1, R2, and R3, we notice that we get 16 volts, which is exactly the source voltage. Again, this is no coincidence. In a series circuit, the sum of the voltage drops across the individual resistors is always equal to the source voltage. Expressed in a formula, voltage total equals voltage 1 equals voltage 2, etc. Another thing that we notice is that the voltage drop across the resistors is proportional to the size of the resistor. Again, this is no coincidence and is always the case. Since R2 is 5 times larger than R1, the voltage drop is 5 times as large across R2 as R1. Since R3 is 10 times larger than R1, the voltage drop is 10 times as large across R3 as R1. If we look at this circuit, it becomes obvious why series circuits like this one are referred to as voltage dividers, as the source voltage is divided up across the individual resistances. Now let's see if we arrive at the same values using Ohm's law as we did with the meter. We look at the same circuit, but we remove the meters for clarity. Remember, the total resistance in a series circuit is the sum of the individual resistors. So, total resistance equals 100 ohms plus 200 ohms plus 1,000 ohms equals 1,600 ohms. To find the current, remember it's the same everywhere in a series circuit, we use I equals E divided by R equals 16 divided by 1,600 equals 0.01 amps. Now to find the voltage drop across each resistor, we use E equals IR. For R1, 0.01 times 100 equals 1 volt. For R2, 0.01 times 500 equals 5 volts. For R3, 0.01 times 1000 equals 10 volts. Great, we get the same results as we did with the meter. Now let's take the same components, but this time arrange them in a parallel circuit. Let's take some voltage readings using a voltmeter. Using a voltmeter across R1, we measure 16 volts. Using a voltmeter across R2, we measure 16 volts. Using a voltmeter across R3, we measure 16 volts. So we see that the voltage across each resistor is the same as the source voltage. Again, this is no coincidence. In a parallel circuit, the voltage across every resistor is always the same as the source voltage. Expressed in a formula, voltage total equals voltage 1 equals voltage 2 equals voltage 3, etc. Let's take some current readings using an ammeter. The current through R1 equals 0.16 amps. The current through R2 equals 0.032 amps. The current through R3 equals 0.016 amps. The current through the whole circuit equals 0.208 amps. Here we see that the total current is equal to the sum of the currents through each one of the resistors. Again, this is no coincidence. In a parallel circuit, this is always the case. Expressed in a formula, I total equals I1 plus I2 plus I3. What we observe makes it clear why a parallel circuit is also known as a current divider. It has divided up the total current over the 3 resistors. Note that the smallest current flow is through the largest resistor, which makes sense since resistance is the opposition to current flow. Next, we measure the total resistance with an ohm meter. Note we first open the switch because you can't take resistance readings when voltage is present. We see the meter measures 76.92 ohms. Now let's see if we arrive at the same values using Ohm's law and the parallel resistance formula as we did with the meter. We use the same circuit as before, except we remove the meters for clarity. We calculate the total resistance using the formula 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. 1 over R total equals 1 over 100 plus 1 over 500 plus 1 over 1,000. 1 over RT equals 0.01 plus 0.002 plus 0.001. 1 over RT equals 0.013. And 1 over 0.013 equals 76.92 amps. We see that this is the same as what we measured. Now we also see that the value is less than the smallest resistor, which is the rule of thumb. Now we calculate the current through the whole circuit and through each resistor. IT equals E over RT equals 16 divided by 76.92 equals 0.208. I1 equals E divided by R1 equals 16 divided by 100 equals 0.16 amps. I2 equals E divided by R2 equals 16 divided by 500 equals 0.32 amps. I3 equals E divided by R3 equals 16 divided by 1,000 equals 0.16 amps. Good. Ohm's law produces the same results we got using the meter. We can also calculate the total current by adding the individual currents through each resistor. IT equals 0.16 plus 0.032 plus 0.016 equals 2.08 amps. Again, we get the same results as we did with the meter. Power is defined at the rate at which work is done. The formula for power is power equals I times E, which is called Watt's law. Another way to look at it would be to say that it's the rate at which energy gets supplied or used up. The more work done in the shorter amount of time, the more power is consumed. But we won't go into that today. We'll save that for the next video. This has been Huckleberry. Thanks for watching. Hope you liked it.